Welcome, friends. Welcome to my academic program. Last day, we have discussed regarding the general overview of power system. Now, today, we shall discuss about the transmission line. What is transmission line? It is the backbone of the power system. It is the line through which we can send our power from generating station to the consumer terminals. Two modes generally are there of transmission of power. One is high voltage AC, another one is high voltage DC. Both are having some advantages and disadvantages. Now in transmission system, we often face some terms like conductors, then transmission towers, then insulator. They are the very major components associated with the transmission system. We shall discuss one by one. Now, how can we model a transmission line mathematically? What is the equivalent circuit? Suppose a current carrying conductor is carrying a current. Okay, suppose a current carrying conductor carrying a current. So whenever a current carrying conductor is carrying a current, by the property of the material itself, it will offer some resistance to the flow of current. So in order to take the resistance effect, a resistance is equivalently presented. Proceeding further, if a current is flowing, a magnetic field will be set up. Okay, and due to that magnetic field, a flux will be set up, and in order to account that flux, we have a inductance is represented. So these two, R and L, will form a series impedance. R and L will form series impedance, which is equal to Z is equal to R plus JX, where R is the resistance of the conductor and X is the reactance of the conductor, which is equal to omega L, which is equal to omega L. Now coming next, now what is this capacitance? Now this is the transmission line. Okay, we have a certain voltage impressed on it and we have ground. So we know when two metal plates are being separated by a potential difference V, and in between the medium is acting as a dielectric, then this entire arrangement is called a capacitor. So with the conductor and the ground, this is ground, with the, so in between AR is there, which is acting as a dielectric. Then therefore this entire arrangement from the conductor to the ground, this entire arrangement is treated like a capacitance. So a capacitance is shown across the line conductor and the ground. So this is our third element. And what will be the fourth element? Now this conductor and ground, we have a potential difference existing, so a current will be flowing in this direction, which is called leakage current, IL, leakage. This leakage current, maybe it is very smaller in magnitude, maybe in the order of microampere or nanoampere. However, it will continue to flow due to this potential difference existed. So in order to take this effect, a shunt conductance is represented. So this C and G will provide shunt admittance, which is equal to Y is equal to G plus JB, which is equal to G plus JB. Sorry, this should be equal. Y is equal to G plus JB. So again, A conductor is carrying current. By the property of the material itself, it will offer some resistance. In addition to that, a current will be flowing, so a magnetic field is created. In order to take that account, an inductance will be formed. These two will be acting as a series element, which is equal to Z is equal to R plus JX. And we have a capacitance formed between the conducting material and the ground, in between here acting as a dielectric. So this C and G is in order to simulate the leakage current effect. So this C and G altogether will constitute shunt admittance, which is equal to G plus JB. Now, as this leakage current is very small, this affects nothing. Okay, so it is always neglected. This current is always neglected. So R, L, C are the three elements considered for transmission line. G is not considered because this leakage current is so small, their effect is negligible. So R and L constitutes the series element and C will constitute the shunt element. So basically a transmission line can be modeled by a series R, then L. This will constitute a series element. This is Z. After that, a capacitance is represented in parallel to that. It is forming a shunt admittance. So if this section is spread throughout or is distributed throughout the length of the line, then this element is called distributed element. And if this value, this Z and Y is considered to be the lumped at one point of the transmission line, it is called lumped parameter. So equivalent transmission line model can be represented by a series RL with that parallel capacitance. Now let's say coming to the conductors, we have three types of conductors. Solid conductors like this, solid conductors. Okay, it is generally not used because of many reasons. Cost will be huge. It is difficult to carry. Likewise, for many reasons, solid conductors are not used. Next, we have stranded conductors and bundle conductors that will be widely used. Now, what should be the conducting materials? It should have low specific resistance in order to provide or in order to offer low value of resistance, high tensile strength in order to withstand mechanical stress, low specific gravity, that means weight per unit volume should be low, and of course the conducting materials is designed such a way that the cost will be lower. Okay. Now what is stranded conductor? Now this is the typical diagram of a stranded conductor, practical diagram, practical conductor. And now this is the cross-sectional view of the stranded conductors. Now this is a overall conductor. Okay, this is a overall conductor. Okay, having radius R. Now this each subconductors will form a strand. That is why it is called stranded conductor. Each subconductor will be called strands. Now this n number of strands, are running parallelly. Okay, they are electrically parallelly connected and they are spiraled like this. Okay, are you getting? They are spiraled like this. Now ACSR is mostly used conductors. ACSR stands for aluminium conductor steel reinforced. This is the most widely used in conductors available. Why it is used? Mainly to achieve uniform current density. Why? I am coming to that in a moment. Now there is a definite formula available. What is the number of strands? There is a formula, it's called 3n into n plus 1 plus 1, where n is the number of layers. Now this central conductor is 1. Now you see, if you come to the first layer, this is the first layer indicated by blue, this is the first layer. Now if you put n equal to 1, you will get capital N is equal to 6 plus 1, that is equal to 7. 6 plus 1, that is equal to 7. So this one is always, this one stands for the central conductor. So with respect to the central conductor, we have 6 conductors have in our first layer. Then if we put n equal to 2, then we shall have 12 plus 1. So this is 2, 2 plus 1, 3, 2. So we have total number of strands available 12. So in this way we have number of strands available in different layers. Now this is a practical data. So if we have a 400 kV transmission line, we use ACSR moves. This is the nomenclature. Now what is the size of the conductor? Now this is the central one and the first layer 6. This 1 plus 6, 7 layers are made of steel with a diameter of 3.53. And out of this first layer, external to the first layer, every conductor is made up of aluminium, and the total number of conductor is 54 and the diameter of them is 3.53 millimeters. So aluminium and steel reinforced, that means central conductors are steel, that is the central conductor, and the first layer conductors are steel as mentioned by blue, they are steel. Okay, and outer conductors are made up of aluminium, both having same dimension, that is 3.53 millimeter. Now overall diameter of the conductor is 31.77 millimeter, and it can carry a mass, or it provides a mass of 2004 kg per 1 kilometer length of the line. Now let us coming back to the higher rating of the transmission line, that is 765 kV line. It is called ACSR Burmese. Now it has certain different strategy of calculation. We have 7 conductors steel, that is there we have diameter each 2.54 millimeter, and external to that steel we have aluminium conductors. Now this time number is reduced, 42 number, not 54, 42, but you can see that their diameter is 4.57. So the steel conductors and aluminium conductors, they are not same dimensions. Overall diameter of the conductor is 35.04 millimeter, and their specific weight is 2181 kg per 1 kilometer length. So aluminium conductor and steel conductor may have the same dimension, may not have the same dimension. It depends on the rating of the transmission line you are installing them. Now what is skin effect? It is a very important term. What is skin effect? Suppose this is a solid conductor. So if a current is flowing through this, a tendency of the current flowing through this only the peripheral part, because the magnetic flux is not uniform in case of a AC current. So current has a tendency to come outside of the and flowing through the periphery of the conductor. So that is why this effect, since the current is flowing through the skin of the conductor, that effect is called skin effect. So it has a tendency to flow to the outer filaments. Definitely what will be happening? The current density will be reduced. Why? Because this inner portion of the conductor is not being utilized effectively. So current density, that is J, that is current per unit area, that is reduced. So if the effective cross-sectional area is reducing, then you know a formula R is equal to rho L by A. So if the current cross-sectional area is reduced, then resistance of the material will be increasing. So AC current, resistance for the AC current is larger than that of DC current. That is the reason. So that is the problem. So in order to avoid the skin effect, we adopt stranded conductor like this. So each strands, I pardon for my drawing, each strand, if there are n number of, suppose this is current carrying capacity is I. If the current carrying is capacity is I for the stranded conductor also, and if there are n number of strands, so each strand is conducting current I by N. Each strand is conducting current I by N. So still this much amount of current is flowing through the periphery of each conductor, but this time the conductor or the current has been uniformly distributed. So effectively entire cross-sectional area is utilized. So this is how we can increase the current density and we have the uniform current distribution. Now with increase of frequency and with the increase of diameter, skin effect increases. So it is a bad effect, we should avoid skin effect. Now let us coming to the transmission towers. We should come to the transmission tower. This is a rough sketch of a transmission tower. We have certain specification. Now at the topmost point, this is the place. Through this, it is called ground conductor. It is in this place, ground conductors are being installed. The purpose of the ground conductor to protect phase conductors. So this place, this place, this place, this place, all their phase conductors are running parallel. So there are 1, 2, 3, 1, 2, 3. So 3 phases. Let us say phase A, phase B, phase C. This is the one circuit. And we have the right hand side circuit, small a, small b, small c. They are running parallelly. So this type of circuit is called double circuit line. This type of circuit is called double circuit line. Now we have certain specification. You see W1, W2, W2, they are the length of the cross arms. They are the length of the cross arms. Now we have the ground clearance H4, it is very vital. H4 is the ground clearance. H1 is the clearance between topmost live conductors and ground conductors, and H2, H3 are the clearance between any two phase conductors. Now we have a very important term, it's called tower footing resistance. It is the resistance through which the tower is connected to the ground. The value of the resistance should be low in order to prevent back flashover. What is back flashover? I am not discussing right now. It will be coming to the subsequent to this in this program, in this course. Now let us having some practical data. Now we have this is very important, we have 3 types of transmission lines: A type, B type, C type. What are they? Now A type transmission lines are those, or transmission towers are those, where angle of deviation is only within 2 degrees. B types are those which are angle of deviations are 2 to 15 degrees. And C types are those angle of deviations are within 15 to 30 degree. And beyond 30 degree, it is another type D. It is maximum deviation up to 60 degree can be possible. Now what is the angle of deviation? Suppose today a transmission line is erected at this place. Now whatever the next transmission tower which will be erected having some span length, now due to some space constraint it cannot be erected straight. So some angle needs to be created. At some angle the next tower has to be installed. So this angle, this theta, this angle is called angle of deviation. So if it is a 0 to 2 degree, then it is called type A tower. If it is a 2 degree to 15 degree deviation, it is called B type tower, and 15 to 30 degree deviation, it is called C type tower. We have certain specification available. This information has been used from the book Electrical Power Transmission and Distribution by these two authors, published by Pearson. Now we have a very important term, it's called right of way. Suppose the transmission line is erected at this place. Now with respect to that transmission line, few spaces around the transmission line should be kept unengaged or should be kept vacant for maintenance purpose or maybe some commissioning purpose, whatever. So this space is called right of way. As this is very important term, you should know. So till now, with this I am concluding here, I am ending there. In the next lecture we shall start the parameters of the transmission line. Thank you. Hope to see you in the next class.